everyone. This is the fourth IITT. This time it's on environmental geotechnics for TC215. And as you know, this is a series of talks that brings together engineers from around the world. And this time we have three speakers to tell us about environmental geotechnics, global ideas, from different perspectives, different part of the world. And as the president of ISSMGE, I'm so happy this is becoming a successful initiative. And I like to start by introducing the three speakers. We have with us Professor Katsumi from Japan. He is the professor and dean of Graduate School of Global Environmental Studies in Kyoto University, vice president of ISSMGE TC215 on environmental geotechnics. He's the vice president of the Japanese Geotechnical Society. He's known for waste landfills, management of contaminated sites, as you read here on the slide, and use of byproducts in geotechnical application, geogenic contaminations, and disaster recovery. Also, Dr. Nikolo Guarena from the Polytechnic University of Turin in Italy, known for his research on coupled chemohydromechanical behavior of active clays, use of geosynthetics for contaminated liquids, mechanical behavior of waste materials. And our young speaker for today is Dr. Susmita Sharma, assistant professor in the Department of Civil Engineering at the National Institute of Technology, Meghalaya in India. And she is also helping with the Technical Oversight Committee as vice chair with ISSMGE. She is known for her research in utilization of waste, biostabilization of soil sediments of wastewater treatment plants, WWTPs. Now, if you unshare the slide and we can see your faces, I have to mention that my background is not fake. I am actually in India, Susmita, in Cochin today, but you're in the north, I'm in the south.
Yes.
I was attending the conference here. I was hoping to see you here. Maybe next
time for sure. Yes.
So I'd like to give the floor to our main speaker, Professor Takeshi Katsumi. Please go ahead. We're so eager to know about this very important subject. As you know, the whole world is changing, and some, especially the young, are blaming us for ruining Mother Earth as engineers. So we have to tell them that we are here to save the Earth from the expansion of the human carbon print. So the floor is yours. Thank you for joining, all of you. And I'm all ears as well, all the audience.
Thank you, Marc. Let me share my screen. Do you have my slides on your PC?
Yes.
Thank you. And thank you for the introduction, Mr. Dr. President. I'm very pleased to join this interactive technical talk as a representative of TC215 on environmental geotechniques. Now, let me briefly speak about my general view of environmental geotechnics, having two presentations by Nikolo and Susmita. I have prepared one slide showing a brief history of the activities regarding the environmental geotechnics and the ISSMGE. Although there were several researches and engineering achievements before this year, but I started this list with this year, 1977, because the first technical session dedicated to environmental techniques was organized the conference, international conference at Tokyo. And following this, the Italian and Japanese professors in Benelli and Western, they presented their very comprehensive report on environmental techniques at the international conference, Stockholm. This report was 60 pages long, covering a wide variety of environmental techniques. We are happy that it is available from the ISSMGE online library. And after that, technical committee number 5 was established on this topic, in which discussion on the definition of environmental geotechniques is initiated. This technical committee is now renumbered as 215 because of the new numbering system under ISSMGE. And more importantly, 2 different conference series have been organized on the topic of environmental geotechnics in ISSMGE, namely ISEG, International Congress on Environmental Geotechnics, which covers a wide range of the topics related to the environmental geotechnics, while SHPEG, Symposium on Coupled Phenomena, which rather focuses on the mechanisms of several phenomena in various types of geoenvironmental applications.
I like this historical background. First time we do it. Maybe it should become like a standard.
Thank you. And we should add some other activities of other technical committees like mining waste or energy, or even others might be related to the environmental geotechnics.
Every episode we're improving, so it's good.
Thank you,
I'm
Marc.
taking notes. Keep going.
Okay. As you know, the environmental geotechnics deal with various types of environmental issues. It's right here. And among these issues, ISSMGE has an independent and strong technical committee dedicated to mine tailings, nuclear waste storage, and thermal and energy issues. And I would say waste landfills, the groundwater contamination and remediation, and the use of byproducts might be the major issue of the environmental geotechnics. And to deal with these issues, proper knowledge of almost all the subjects of soil mechanics and geotechnical engineering are required. As examples in this table, in which I have listed the subjects of soil mechanics in relation to the issues in the waste landfills. For example, knowledge of permeability is essential to understand the contaminant transport, either in the clay barrier system or in the surrounding subsurface. Settlement due to the surcharge of waste reclamation is evaluated based on the fundamental knowledge of soil compressibility and consolidation. And this photo is trying to show the installation of a compacted clay liners before compaction. The compaction is primarily important to design and install the barrier area to prevent the groundwater contamination. In our country, we have several projects regarding the land use of closed landfills, in which the proper assessment of bearing capacity is essential. And we also know that the stability issue sometimes causes catastrophic disasters which should be prevented by using the proper knowledge of slope stability and waste and flow mechanics. So to deal with these issues, we design or evaluate based on various indexes such as the concentration or mass of the contaminants, the mechanical stability or safety, or total volume of a resource utilization, cost effectiveness, or land use opportunities, greenhouse gas emission or carbon emissions, and so on. So therefore, it might be difficult to reach one solution with one single index. Detailed and comprehensive assessment is necessary. Because of them, I'm sure that the geotechnical engineer has been playing an important role in various types of environmental issues, sometimes together with the professionals from other fields. Okay.
Thank you. This is a very important message that we shouldn't be limited to one specialty. A good engineer should have broad knowledge. Yeah, keep going. No worries.
Thank you, Marc, for your comments. So now this slide is trying to show one of the important topics dedicated to the environmental geotechnics, which is soil-water chemical interactions. Since numerous studies have been conducted by many researchers on clay chemical interactions, particularly for clay liners with a hydraulic conductivity and barrier performance, which are affected by osmotic sweating, membrane behavior, or construction quality control, or sometimes amendment methods such as modified clays. And these issues are researched mostly for clay liners and barriers, but such knowledge about solid chemical interaction is necessary for other applications in environmental geotechnics, such as in-ground wall to contain the soil and groundwater contaminant, attenuation layer for the embankments of the contaminated soils, and so on. Recently, researchers and engineers have started to work with the chemicals such as PFOS or P4, which are considered emerging chemicals in environmental engineering. And they are developed in the 1940s actually and have been utilized in many applications, particularly as a very effective firefighting foam, but toxicity have been recognized only several years ago. These chemicals have both hydrophobic and hydrophilic sides. Understanding their behavior in subsurface is a great challenge, as well as establishing a proper testing method is also of great importance because of such characteristics. And our team has just started several fundamental researches, such as absorption behavior of typical types of local soils, as indicated in this graph. Here we have plotted the absorption percent for local soils against the PFOS, and we'll be trying to discuss the effects of soil type and specific fraction on absorption behavior. We'll try to link these fundamental works.
Sorry to interrupt. Yeah, if you can zoom the screen onto the graph that you explain. So and explain that.
I don't know.
I don't know if you don't have to really zoom, but as you're explaining, so the sorbed amount, sorbed amount is like the absorbed amount going through a layer, or if you can explain more,
sorbed
because
amount.
I can, yeah.
soft amount is the PFOS attracted of the soil particles and will not transport by the movement of the water, so trapped on the soil. So if we have a high amount of soft fraction, our PFOS will remain in the soil and will not move to transported with the groundwater. So we may not have a severe groundwater pollution problem, but we might have the problem with the soil pollution or soil contaminations.
So the soil becomes more polluted when the number is higher.
Yes.
And if the number is lower, it means most of the contaminants are being taken by the water.
Right.
So
but the PFOS will not disappear. So therefore, PFOS will exist either on the soil or water side.
Or in the water.
So what we have to...
So globally, is it better to absorb it by the soil and then treat the soil, or it's better to keep it?
It depends on
the best is not to produce it.
It's too late. We have produced and distributed to the environment already. So the issue is to understand the behavior of PFOS, where PFOS exists. And if the sorption is strong of the specific soil, we should attack the soil, like the soil excavation or soil purification by using some chemical method. But if the sorption capacity of the soil is not strong, we have to look at the surrounding, the downstream groundwater, whether our PFOS is reached to the very far downstream and affect the drinking groundwater or not. So
one more question. One more question. The blue, because we have 4 types of soils here. The blue would be the sandy, gravelly, cohesionless. Or
yes.
So the finer the material, the more absorption of the contamination. So the red line would be some sort of clay.
Red line is
the higher the line.
Okay. Generally, if we have finer fractions, we have more soft amounts. And also, if we have the higher organic fractions, we have higher soft fractions. So this time, I'm lazy. I did not prepare any slides indicating the basic properties of the soils. But what we have obtained through these data is at this moment, it's difficult to derive the clear the conclusion based on the soil type or soil, some specific fractions. So therefore, we need more research. But what we like to say is that the sorption isocymes can be obtained by our health skills. That's our first step.
Thank you. Can move on.
Thank you. So now let me share with the one Japanese case with you. Although it's a local case, but it can be a universal topic to be implemented in other places in the world, which are prone to the severe natural disasters, and also applicable to the remediation of illegal dumping sites. The 2011 East Japan earthquake and tsunami, about 30 million tons of disaster waste were generated. A large fraction of the soils were included in disaster waste. We have succeeded at treatment of such soil waste mixtures to recover the soils and utilize them in several applications in the disaster recovery work, with significant technical contributions by the Japanese Geotechnical Society. These recovery works for 20 region disaster have been completed, except for the issues of a nuclear accident. And we found that there are still needs to develop the better and more efficient treatment method to recover the soils. We have to recover the soils more in terms of the quality, and also high purity of the soils is required, because we are not quite sure whether the remaining waste fraction have any adverse effect on the recovered soils. This photo shows the procession of the crystal embankments using the recovered soils from disaster waste. And this black color and black was possibly due to the waste wood fraction remain in the recovered soils. So we will see carefully more about these anaerobic effects, and also might have better to establish more suitable method to obtain the better quality, more pure of recovered soils. That's one of our challenge right now. So can I move on to the next slide, which is the final slide? Let me summarize my presentation now. The further research is particularly for soil and water chemical interactions, not only in terms of the contaminant transport, but also other aspects such as the stability and soil and land use are necessary and fruitful academic achievements with experimental, theoretical, and analytical approaches are expected. And based on these achievements, we are expected to establish the proper testing method to evaluate the state of contamination, design of geoenvironmental facilities or projects, or estimate the future risks which should be properly managed. And also cost-effective countermeasures such as remediation, containment, mitigation, or treatment of recovered soils, as indicated in the previous slide, will also be based on the scholarly achievements, including the soil water chemical interactions. And we are likely to look at one specific facility or one specific phenomenon, but the system to monitor our entire facility or entire project and accumulate, analyze, and utilize the data of monitoring obtained from multiple projects is also important with the help of modern technology of ICT or AI. This kind of system will be utilized to enhance our technology or idea for the future. And I have indicated that the geotechnical engineers play an important role, but our environmental projects usually will not be possible without the cooperation of the professionals from other peoples, and communication and involvement with individuals and institutions are also needed to implement our idea into practical works. So I expect many professionals and many professionals of environmental geotechnics, either young or senior, will enjoy these challenges. So this is the summary of my presentation. Thank you.
These are not challenges. These are more like must do,
right,
as and geotechnical engineers for, you know, a successful mission.
Yes.
Okay.
Not
I
only
think we can Thank you so much. This was so informative. I think we can give the floor to Nikolo.
Okay, probably Susmita asked to speak as a second, but not sure. Well, what do you prefer,
As you like.
Susmita?
Go ahead, Susmita. Are you ready?
You are muted.
Yeah, I'll share my slides.
Okay.
Yes, go ahead.
I go
All
there.
ears. I think
Is my
Nikolo
slide
went
visible?
to the same. Ladies first.
Okay. Thank you, everyone, for providing me an opportunity to speak on this interactive technical talk. I am Dr. Susmita Sharma, and today I'll mostly speak about a continuation what Professor Takeshi have already highlighted, soil-chemical interaction. So I would like to give a small example, and I'll start what actually triggers me for today's talk. So as mentioned in the previous slides by Professor Takeshi, so from a scientific standpoint, it can be seen that in most of the developing countries, so on an average or with the countries with mixed economy, so even though municipal solid waste landfills are in practice in paper, but then in practice, we have open dump yards or like unsanitary landfill. So what happens actually in this unsanitary landfill? This is where your soil contamination, water interaction takes place. So in the municipal waste facility, so the most important or the pressing concerns for environmental or the municipal engineers is the leachate generation, first of all, and the landfill gas generation. Now, which is more contaminating, either the leachate or the landfill gas generation? So there is no debate on that. It's equally harmful for the ecosystem, because once the leachate is generated, it contaminates the soil, it contaminates the groundwater, and the nearby ecology of the place is destroyed because of excessive eutrophication. So environmental risk scenario associated with the landfill is too much. So mostly in, as I said, it is in two phases, so liquid and the solid phase. Now, translating this to a current state of affairs, that is a landfill which is there in Delhi. So this is information that I have got, recent information, so which has been shared. So this is the status of a Gazipur landfill in Delhi. So it started 2010, the pictorial view from 2000 onwards to 2022. So you can see that the landfill is almost now 65 meters in height. So all of you are aware of how much tall. All of you are aware of Taj Mahal, right? So Taj Mahal is around 73 meters high. So this landfill is slightly closer to Taj Mahal. So this is the problems that this landfill is experiencing. Now, in addition to this, the small ecological or social impact because of this high standing landfill, it is like in the recent times, there have been 4 times where fire broke in the landfills. Then air quality index in and around the landfill area is very bad. So this landfill is situated in Delhi, which is the center of most
Susmita,
of the economic. Yes.
do you know how many years it took and was there to reach the 65 meter?
This landfill, if I'm not wrong, was commissioned in 1982. This was supposed to be closed in 2002, but until now, this is operational. So every day, around 3,000 metric tons of municipal solid waste comes here.
Wow.
I think the number of the trucks that brings it close to 700. Now, because of this, what has happened was, like there were 2 people killed as well. And I think 4 of the trucks, as per a recent report, had fallen in drains, and then it toppled while it was going to dump the solid waste into this landfill. So in addition to fire hazards,
And is this a
in and around
controlled
the
landfill? Like, is it sealed at the bottom or
no,
this not?
it is. No, it is not. Partially, this is not a sanitary landfill. As per the reports
Wow.
that is being said. So, and I'll show you the next slide, which is associated with this. So you can see this is also the continuation of the report. So most of the reports I have information I have collected from Central Pollution Control Board websites and NGOs which have published. So you can see the leachate which is getting generated. So this is the dumping trucks. This is the leachate getting generated here in the collection bins. Now, as we are all aware of it, what happens when the leachate generates is dissolved oxygen in the form of your chemical oxygen demands or total organic compounds, volatile acids. Now, these municipal deposits, municipal solid waste deposits also gets types of the waste such as like construction and demolition waste, then industrial waste and sludges also. Now, as a result of which, what has happened is inorganic microcomponents in the leachate also increases. Then we have very high heavy metal concentration in the leachate water. So as per a recent report submitted, so there is a concentration ratio of heavy metals, which is there in here, which is being compared with the water extract available from the local soil. So they have found out that very high concentration ratio of chromium, nickel, copper, zinc. Yeah, chromium, copper, zinc, then arsenic, selenium, cadmium, and lead. So these are the commonly, these are the reported concentration ratios of heavy metals in the water extracts nearby. Along with that, the xenobiotic organic components like aromatic hydrocarbons, phenols. So these are common, depositions, which is being found in leachate generation in case of unsanitary deposits.
Do you know if
now,
this water is flowing towards the ocean or it's somewhat being contaminated or,
yes,
I mean, contained?
Yeah, as per a report submitted, I think this year, starting of this year, I'm not exactly sure with the date. So National Green Tribunal actually they have issued regarding pollution of the nearby water body. So they have issued a notice. So I'm not exactly sure to put it here.
This is
but there is
so heartbreaking. This
yes.
is crazy. Keep going, Susmita. Sorry to interrupt.
Yeah.
Want to be interactive.
Yeah.
Talk.
So yes. So when these type of the leachate, I try to look into the research. So there has been challenges like which also has been found out. What happens to the leachate when it ages? Now, most of these, in case of the developing and the underdeveloped countries, so the leachate generally changes with age. Like say if it is a 20 years time frame or 30 years time frame. So what happens is the characteristics of the waste completely changes. So biological oxygen demand, as you can see, if it's an old leachate, so I have like highlighted it with blue, yellow, and orange or on pink colors. So you can see when the leachate is very young, so the ratios of its chemical component is very high. So the moment leachates become older, so it stabilizes. Now, why it stabilizes, maybe I will discuss in the coming slides what happens to the stages of the leachate transformation. So these are the characteristics of the leachate. So mostly biological oxygen demand and chemical oxygen demand. Then the extent of biodegradability. So once the organic stage is, aerobic stage is converted to anaerobic stage, so most of the biodegradability component of the leachate is already attained. So this is where the biodegradability becomes very, very low when it becomes an old leachate. Then we have pH. Now, initially the pH is very high. And then when it becomes, initially the pH is very, very low because acidic formation takes place and then later it stabilizes. So there are different treatment techniques also which I could find out depending on the extent of the contamination or depending on the extent of the chemical attributes of the leachate. So the leachates are treated with the help of biological treatments, then chemical treatments, then physical chemical treatments. So these treatment policies are mostly adopted based on site-specific need of the leachate that is being investigated. Now, this was one of the problem. Yeah. Yes.
Can I interrupt you? The interest
yes,
data, and you have shown us the properties of the landfill leachate by dividing old, medium, young, and old landfills, it's more than 10 years. But to me, 10 years might be short still.
Yes.
So do you have some sites in which the data was collected for longer than 15 years or 20 years in your country?
Right now, I do not have it, but yeah, I'd like to take that point into consideration. Maybe if we have another presentation like this, I'd like to show what happens from the day 0 to day 30, I think. So I'll take that note. I'll take a note of that, Professor. Thank you.
Thank you. Thank you. Keep going.
Can I move? Thank you. Okay. So the first aspect of the environmental risk scenario in landfill that we have just now spoken is about contaminated leachate. The second aspect is the generation of gas, so in the municipal solid waste landfills. Now, this is another example of what happens when municipal solid waste landfills get different types of unsegregated waste. So mostly in developing countries, as we know, the type of the waste that is being deposited is higher type is the organic in nature. So this type of the waste, what happens is once it starts degrading, so it generates carbon dioxide and methane. So mostly near around the leachate landfill area, so it creates a smog. So how do we take care of that particular, this particular problem? So recovery of the gases, which can be combusted and which can be, again, waste to energy concept. This is where it comes from. So from the waste, if energy can be harvested in the form of methane gas. So in many of the sanitary landfills, this is possible, waste to energy concept harvesting. But then in most of the unsanitary landfills, what has been seen is they generally flare the methane which is generated. But when it becomes an uncontrolled deposit, so flaring at times is it's not satisfactory, and this is where fire outbreaks happens or fire hazard happens in landfills. So moving ahead.
This happened.
So,
this happened to me one time.
Yes.
This
yeah.
happened to me. Yes, I had a team drilling boreholes in a landfill that was getting ready to be treated in Beirut, and they started smelling methane. And one guy was smoking a cigarette. He didn't know, and we had a big fire. wasn't very pleasant. Keep going, Susmita. This can happen.
So,
can I say the smoking at landfill is strictly prohibited because of the fire accident, and the fire will not be disappear until all the waste will become fire. So it's dangerous.
Yes. There are some landfills that were covered and they keep chimneys flaming continuously.
Yes.
They became, I think, a park. I forgot the region, but maybe you can help me. They covered it and they planted grass, and looks nice, and you can see chimneys flaming all the time.
Yeah.
Keep going.
Okay, thank you. So once the municipal solid waste gets deposited in the landfill, what happens there? So the municipal solid waste, the biocomponent of it has to get stabilized. So how this stabilization and ultimately it results in the production of landfill gases. So this entire process of stabilization actually happens in two stages. The initial portion is your aerobic stage, and the later one is the anaerobic biodegradation. So what dominates in the prior part is the aerobic, and later the methane generation, which is mostly significant, is in the anaerobic degradation of the waste. So I would not like to go like details of all the phases, but some highlighting points that I'd like to mention here. So phase one is the state when the waste just enters the landfill. So the moment the waste enters the landfill, what happens is there are a lot of voids which is present in the waste. A lot of oxygen is available, molecular oxygen is available there. Now, as a result of which, it gives an abundant opportunity for the microorganisms or the populations to grow. Density of the microorganisms increases, and they try to acclimatize to the changing scenario. Now, they take the oxygen and with the continuously added and the compacted waste, what happens is over the time, the oxygen content of the landfill decreases over here. Now this leads to the phase 2, that is the transition state. Now decreasing oxygen level, what it leads to is lesser aerobic degradation and more aerobic conditions to be generated here. So since this aerobic to anaerobic transition happens, so oxygen gets readily displaced by carbon dioxide as an affluent gas in this system. So as you can see here, the peaks are increasing for carbon dioxide stays here. So maximum carbon dioxide deposition happens. Now the third phase, yeah.
Sorry to interrupt, but this question for you and the other speakers, can we put some sort for the audience, some sort of years per phase? So plus or minus, I mean, how many years it takes to finish the aerobic, and then for each phase of the anaerobic. Do we have any estimate or idea?
Generally,
Professor,
during the first, okay, sorry. Yeah.
Go ahead, yes. I mean, whoever can give us just for clarifying its phase in terms of time, because I'm assuming it's related to time.
So what is mostly seen in the literature is like the first decade is the one which the methane starts generating. So it's first 10 years.
Okay.
And then after 30 years, like it almost declines to a negligible amount, but that depends on if the landfill is closed. But if it is a continuous deposition, so like the 30 years is not the amount where the decomposition or the stabilization phase of the MSW is reached.
Okay, keep going.
Okay.
You have
so
to go a bit faster.
Yeah. Yes. Okay. So the anaerobic phase is mostly about the acid formation. What happens there is the pH of the leachate drops down significantly. Organic acids gets developed. Then it leads to the final phase, that is your methane fermentation phase. So all the what you call or decomposition biodegradable materials, they are converted to either methane or carbon dioxide by methanogenic bacteria, which is mostly an anaerobic form of bacteria which is available there. So this is about the production of the landfill gases. Now, this is another like phases of the solid waste decomposition, how it happens, like the gas compositions by volume, the characteristics of it, the stabilization times, which is initially recorded, the question that you were asking just now, Dr. Marc, with respect to the characteristics of the waste that is getting dumped in the landfill. So this talks about pH, the amount of the ammonia which is generated. So higher ammonia means higher eutrophication or the ecosystem in and around if it is not a sanitary depot or landfill. So that gets affected. And the final stage is the maturation state. That means it's already, the biodegradable component has already stabilized. So these are the different phases associated with the percentages of gas compositions by volume, the stabilization time, and the characteristics of the solid waste, of the waste which is getting deposited in the landfills. Now, this is another interesting site which talks about age of the waste, which affects the generation of the carbon dioxide and the methane in the landfill. And it has been seen that the age of the waste affects the amount of the oxidation reduction, pH, and other important characteristics of the landfill municipal solid waste which is deposited here. So the physical, chemical, biological conditions of the landfill is the governing parameter which determines the rate of the degradation of the waste. So as you can see here in the slide, so this is a characteristic study, it's not necessarily, it's not from India. So this is information that I have got from Dr. Valero. So he has published this data. So So he has uploaded, he has shown that the methane generation increases and then it's reached to stabilizing point here. So initially during the first few days of deposition, so this is the carbon dioxide generation, which ultimately gets stabilized. So at the end of the day, we have two global warming gases. So this is where the COP agreement, which has been recently signed, so that becomes a concern. Now, how to take care of this? So these are the two pressing concerns which is there in municipal solid waste depositions, pressing concerns of municipal solid waste depositions. Now, what are the futuristic approaches? Now, there are a lot of information which is available, techniques which is available in research, but most of the techniques are not escalated into the ground level. So some of the techniques which is there depending on the type of the waste, segregation not being possible. This is important thing to mention here. So this is the processing facilities and the numbers and the capacity of the processing facilities. One characteristic study of how to reduce landfill loads, like reduce, reuse, and recycle, or waste to energy or waste to compost. These are the futuristic approaches or the current approaches, which is very predominantly undertaken in taking care of municipal solid waste. Now, to give us a concluding remark, what do I have?
Yeah, go back one slide because it's dear to me before the conclusion. I hear our principle every day at home because my daughter is into sociology and environmental science. And we actually, and I'm encouraging everyone on this planet, we actually reached almost zero waste at our house because we listen to the young, and the youth is very important. So the RRR principle, reduce, reuse, and recycle. Recycling should be our last resort, guys. And I'm talking to everyone hearing us. Reduce is when you go to the supermarket with your own shopping bags, not the plastic bags they give you. Buy stuff that is not packaged. The packaging, the nylon, all that is so bad. The plastics. Reuse is when we reuse the material, the bags, the containers. And finally, recycle is when you count on recycling, but it should be our last resort. Composting is also something I started at home. So it all starts with us. And I want to say something here. The earth has always been cleaned. It's us humans that we ruined it and made it bad. We should keep this in mind. And as the president of ISSMGE, I'm putting, as you noticed, more weight on environmental stuff because the old generation used to brag that we built bigger bridges and larger highways and high-rise buildings. And we should stop doing that. We should be more proud of saving an old bridge, saving an old building, reusing the same footprint as engineers. Keep going with your conclusions, Susmita, but this is so dear to me that I had to interrupt.
Sure. This is my last slide. So the concluding remarks, I'd like to put it this way: uncovered dumps of landfill are a landfill of where supposed to be landfill of yesterday, but are still prevalent today. So then compacted covered sanitary landfill, so still remains a landfill of the distant future in most of the developing countries. So with uncovered, uncompacted, unsanitary landfills, so the source of pollutants such as leachate and green landfill gases are continuously getting emitted in the soil, in the air, in the water. So this necessitates a good landfill design to take care of the soil water contamination interaction problems, so that an essential and a safe disposal waste facility can be provided, and in such a way the environment can be, integrity of the environment can be maintained. So this is all I have. Thank you very much.
Very good, very good. I really like it. Thank you so much. Now it's time for you, Nikolo, if you
yeah, of course. I try to share my presentation, just a few seconds.
I like the background you have.
Yeah, it's the main building of our university.
It's beautiful. I have to come visit you.
Yeah, we are proud of that. But there are many other beautiful buildings in Turin. You are invited to visit our beautiful city.
Every time I go to Italy, I'm impressed from city to city. I think it's the richest country in terms of art and history.
Yeah, of course. So each city has its own features, its own history. So it's amazing because also I think as an Italian, I don't know everything about my countries and all the cities. So it's always amazing to also for me to visit new places in Italy and to discover every time new things. So it's really amazing, I think, not just for foreigners but also for Italians.
I was in Reggio Calabria in the very south at your conference, but now it's time to visit the north next year. The floor is yours.
Very, very different environment, very different people, very different habits. You will be surprised on how much difference you can find from north to south to central Italy. It's amazing.
Is the pizza different?
It's our weakness, but it's also our strength in a way. So it's of course this huge diversity among different regions is a kind of problem sometimes, but it's also our strength, I think, because of course no other countries in the world can show such a diversity like Italy, I think.
Go ahead, Nikolo.
Okay, so you can see clearly my slides.
Yes.
Okay, so this presentation is aimed at stressing the interdisciplinary approach of the subdiscipline in geotechnical engineering that is commonly referred to as environmental geotechnics. Although the origin of environmental geotechnics cannot be exactly fixed in time, we can assert that environmental issues have become a significant component of geotechnical engineering since the early 80s, when geotechnical engineers started to be extensively involved in the design of new engineered waste disposal facilities or in the remediation of subsoils contaminated by past industrial activities. Besides the need to broaden their know-how, as the ability to address this kind of issues relies on the understanding of concepts and disciplines that are not included in their educational background. Geotechnical engineers should never forget that their expertise to characterize and model the coupled mechanical and hydraulic behavior of soil-like materials is an added value and probably the most appreciated one when facing environmentally related problems. Such an expertise makes geotechnical engineers unique among other professionals, such as hydrogeologists, groundwater engineers, and environmental engineers, who may be similarly called upon to solve problems related to subsoil pollution. The occurrence of several huge landfill failures in the recent past emphasizes the importance of an adequate understanding of soil mechanics when designing waste disposal facilities. As far as the failure mechanism of landfills are concerned, in addition to the rotational mechanisms that are prompted by soft foundation soils, steep waste slopes, or poor waste compaction, the translational mechanism with the waste mass sliding over the lining system at the base of the landfill has resulted in the largest failures to date. Fortunately, modern engineered landfills are particularly susceptible to failing according to the translational mechanism. Indeed, the bottom lining system, which is aimed at isolating the solid waste and preventing the surrounding environment from being contaminated, is made up of high permeability soil drainage layers, low permeability compacted clay liners, and geomembranes, with the possible presence of many other geosynthetic materials, such as geosynthetic clay liners in place of compacted clay liners and drainage geocomposites in place of soil drainage layers. Even though the use of geosynthetics is certainly desirable, as it can improve the sustainability and the pollutant containment performance of landfills, a number of weak geosynthetic soil and geosynthetic interfaces are created, with the values of the angle of shear resistance that in some cases may be even lower than 10 degrees. The stability of landfills can be further threatened by the morphological conditions of the construction. This latter problem is particularly severe in those countries like Italy and Japan as well, where the high density of population and the numerous seismic, environmental, urban, artistic, and archaeological constraints significantly limit the viable areas for a safe construction of waste disposal facilities. The case history of a municipal solid waste landfill located in central Italy and constructed over a sloping ground is here presented, as it summarizes all the stability issues that have been pointed out so far. The landfilling activities started in 1995, and the geotechnical consultancy was commissioned by the landfill operators in 2017 to assess whether the landfilling activities could continue without the risk of triggering instability phenomena until reaching the maximum authorized capacity. The results of large-scale direct shear tests, which were carried out on representative samples of the most critical interfaces of the landfill bottom liner, pointed out the existence of very low values of the angle of shear resistance ranging from 10 to 15 degrees, which needed to be properly considered in the landfill stability analysis. A series of piezometers was also installed, thereby allowing the piezometric surface within the waste field to be reconstructed. Such a piezometric surface was associated with an excessive leachate head acting on the base of the landfill, as high as approximately 19 meters in some areas of the facility, which was clearly unacceptable not only from the viewpoint of the geotechnical stability, but also from the viewpoint of the release of contaminated liquids into the surrounding environment. Design and activation of a leachate removal system was strongly recommended, whose goal was to lower the piezometric surface until reaching a configuration that was compatible with the minimum safety requirements at the ultimate limit state. On the basis of the results of the stability analysis discussed in the following of this presentation, the maximum allowable leachate head, which had to be reached and maintained for the continuation of the landfilling activities, was set equal to 5 meters. The stability analysis, which were performed using a fully three-dimensional finite element method commercial software, showed that the translational failure mechanism over the bottom lining system was, as expected, the most critical one. In particular, the ability to capture the beneficial influence of the actual three-dimensional geometrical layout of the disposal site allowed satisfaction of the minimum safety requirements to be demonstrated under both static and seismic conditions, provided that the leachate removal system was effective to maintain a piezometric head on the bottom lining system lower than 5 meters. If, on the one hand, the formal educational background of geotechnical engineers represents a solid ground to face the myriad of environmental challenges that continuously arise in industrialized countries, on the other hand, interaction with other disciplines is similarly essential in the multidisciplinary approach of environmental geotechnics. A noticeable example is provided by the recent worldwide spread of the newly emerged coronavirus. Due to the potentially high viral load during the most acute phases of the pandemic, healthcare and medical solid waste, as well as waste streams that are generated from domestic and workplace garbage, pose severe threats to their safe disposal, both in the short term for the employees who are involved in the management of the solid waste and therefore are exposed to the contaminated bioaerosol, and in the long term for the preservation of the quality of the groundwater. As far as this latter issue is concerned, geotechnical engineers, with the cooperation of microbiologists, can play a prominent role in assessing and possibly improving the ability of landfill composite liners to prevent the migration of the infectious pathogen from the waste field to the groundwater, which in turn may represent a vehicle for the transmission of the virus in the environment and eventually again to humans. Even before investigating the interactions between viruses and composite liners, we should bear in mind that specific viral components that are required for infection are naturally subjected to degradation. And thus, we first need to characterize the decay over time of the concentration of the infectious virus, whose survival time in landfill leachates may be significantly shorter than in clean water. When the pathogen transport through the bottom lining systems has to be addressed, the ability of viruses to undergo attachment and detachment processes on the solid particles within engineered clay barriers raises the issue of their survival time in the adsorbed state. According to the limited experimental evidence available to date, the inactivation rate is expected to decrease following attachment to the clay particles, at least under near-neutral pH conditions. Such a decrease in the inactivation rate is ascribed to the deformation of the outer envelope, which allows viruses to adapt their shape to the clay particles, and at the same time provides them with a high mechanical stability that preserves the infectiousness for a longer period of time than the free solution conditions. Last but not least, the ability of engineered clay barriers to act as semi-permeable membranes, that is, the ability to restrict the migration of the infectious pathogen while leaving relatively unimpeded migration of the water molecules, needs to be properly investigated. In the case of montmorillonite-rich clay barriers, such as geosynthetic clay liners, the virus size may be of the same order of magnitude as the pore size, with the narrower pores being therefore inaccessible to the pathogen transport, according to a mechanism that is referred to as steric hindrance. However, the larger pores may also impose some restriction to the migration of the infectious pathogen, according to a mechanism that is referred to as electrical hindrance, as both viruses and montmorillonite particles carry a net negative electrical charge under near-neutral pH conditions. In such a case, the effective pore size accessible to the pathogen transport is significantly smaller than the physical pore size. It is as a result of the overlapping of the diffuse double layers and the development of electrostatic repulsive forces between the migrating virus and the solid skeleton. So with this slide, I concluded my presentation. Please, if you have a question of or you need some clarifications, please.
This is very interesting. Did you diffuse this to the medical experts, like regarding?
Let's see. So as a geotechnical engineers, we're able to benefit from the wealth of knowledge that comes from the medical field. So let's see if also doctors and so people who work in the medical field will be able to benefit from our discipline too.
Very, very interesting. Thank you. I think with this we can conclude our session if you unshare the screen. And
yes,
I don't know if Professor Katsumi or Susmita want to add anything before I close the session. You are muted. Unmute.
Unmute. Thank you, Marc, and thank you for your presentations, Susmita and Nikolo. They are very interesting. And today, both of you made a presentation regarding the waste landfills with different approaches. So we have many issues to overcome, and it's good to share our experiences and knowledges. And we have various similar phenomena or applications. For example, I have the experience to ask for the supervision of the containment of the livestock with influenza, which were killed and buried, unfortunately, because of the disease. And in such a case, we are not sure about the phenomena in the subsurface. So this kind of the knowledge or experience can be shared with from different approaches or different applications. So today I was enjoying your presentations and try to speak with other people about these interactive technical talks. Thank you both of you, and thank you, Marc, for your leadership.
Yes, of course. Thanks to all of you. I like that the three presentations complemented each other and showed that we have problems in different parts of the world. And definitely this is a subject that needs a lot of work, and wish you the best of luck to all of you, and happy holidays. We're coming near the holiday season, and we'll see you around in different conferences, hopefully in person very soon. Bye-bye.